We'll talk a little bit about shrinkage and how this actually works to reduce shrinkage. We'll get into a little bit of the plastic shrinkage stuff, and then we'll get into some of the other properties. I think everybody would agree that cracks happen way too frequently in concrete, and they frequently shorten the service life. What we're really trying to do, it's not actually the shrinkage that's the problem, it's the fact that the shrinkage is restrained or prevented from happening that's the problem, and we generate tensile stresses inside the system. So we could actually work out a whole bunch of equations on why stresses build up in the system and how those stresses are relaxed. But the basic issue is when the stress that develops in the system from being restrained exceeds the strength, we're going to have a big problem. Now, with internal curing, the real issue here is you can actually mitigate a substantial amount of that shrinkage that's taking place, and we'll talk about that for a couple of seconds here. Again, we've talked about this before, that we're essentially moving water from the big pores into the paste. And it turns out that shrinkage is driven by the size of the pore that's being emptied. All right, so somebody would probably argue with me and say it's not the size of the pore, it's the size of the meniscus. The meniscus, which is that little curvature of the water, fits the size of the pore. So let's just say it's the size of the pore. If you empty out a big fat pore, right, pore that's a foot wide, there's no stresses that are generated. If you empty out a pore that's a nanometer wide, the stresses are enormous. All right, we're getting into tens and hundreds of megapascals. Right, so it's the size of the pore that's emptying out. So the whole thing that internal curing does is it fills up those pores and delays or prevents that shrinkage from happening in the overall system. Turns out there's an equation that you can use that says the stress that develops between the two pore walls is equal to 2 times the surface tension of the fluid, for water it's 72 dynes per centimeter, divided by the radius of the pore. So as the pore size gets smaller, the stresses go up. When the stresses go up, the shrinkage goes up. And this is a very simple equation that's been used for years and years and years. Now, what happens is we have the chemical shrinkage that's way up here. We have the external shrinkage that's down here. This is that vapor space that's filling in. And it's that vapor space that's creating those menisci. It's that water tension that's inside of the overall system. So if you had a system that had access to water, when that self-desiccation happens, water just flows into that system, gets sucked into the system like we talked about before. If the system is sealed, you get these vapor spaces that start growing, and they're really going to give rise to that shrinkage in the overall system. Now, I mentioned this before, but this happens every single day, and people watch this every single day. So my father was a contractor. I learned very early that the time to finish the slab is right after that water sheen goes away. You've got time to smoke 1 cigarette and get out and start finishing the slab, right? And the reason is this is when your concrete's starting to solidify, right? It's that solidification that creates that suction pressure. That suction pressure is that same stress I was talking about that's driving the shrinkage, right? So all of these things are related. The idea is the lightweight aggregate has bigger pores, so when we start to get this self-desiccation, water moves from the lightweight aggregate into the overall matrix, and it does this automatically, right? You don't have to tell it, you don't have to yell at the slab, all right? Nothing happens, right? It's the capillary suction that just pulls the water out of the lightweight aggregates. Now, this is a little bit of an unconventional way. This black line is that 7-pound number that we were talking about before. This is the shrinkage of a conventional concrete down here, and each one of these are just putting a little bit more and more lightweight aggregate into the overall system. So if you replace just a little tiny bit here, this is maybe 1 or 2 pounds, you make almost no impact on the overall shrinkage of the system. But as you start adding more and more lightweight, you see you go from a shrinkage into actually creating a slight expansion. And that slight expansion, a lot of times, people spend a lot of time, believe it or not, worried about this slight expansion. You see this all the time. You take a cylinder, you put it in a water tank to cure it, there's a slight expansion. It's a relief of the stresses that are in the overall system. Same type of thing that's happening in here, right? So when you get to that black line, you're really reducing the shrinkage that's in the overall system. The other thing that we did was we built this thing that looks a little bit like a still. I promise you it's not, but essentially what it's doing is it's pumping hot or cold water in through the system. And the idea is we put concrete in between these two pieces of a very special type of steel that doesn't change length when it changes temperature. It's called Invar. We place the concrete in between there, and we heat it and cool it to see what's happening in the overall system. If we've got a conventional concrete, what we'll see here is we have a little bit of heat of hydration, and then essentially what we do is something very mean. At 3 days, we drop the temperature until it cracks. You'll see here that there's a buildup of stress. This is about 300 psi, all right, about 2/3 of the tensile strength. As soon as we start dropping the temperature, the stresses go up and it cracks. When you've got internally cured concrete, what you'll notice here, the big takeaway is the built-up stress is a lot lower in the system, which means that you can have a greater temperature change. So if you just think about this, the conventional concrete, it took a 10-degree temperature swing, 10 degrees Celsius, 18 degrees Fahrenheit, to get thermal cracking in that system. The internally cured concrete took almost 3 times as much temperature variation, almost 60 degrees Fahrenheit, to get the same cracking. So if you happen to be in an environment where you don't have a whole lot of temperature swings, maybe your conventional concrete gets away without cracking, but you've got a lot more belt and suspenders in the system when you're using your internal curing. Right? Again, sort of reducing that stress in the overall system. Now there's a question a little bit earlier about plastic cracking. There's really 3 components to this, and the internal curing is going to work on all 3. It's going to help with autogenous shrinkage. This is shrinkage that occurs in a sealed system. It's going to help reduce settlement, all right, because it's going to reduce the capillary suction that makes the system shrink, and it's also going to help provide water for evaporation. So you can get all these cracks across the system. I once put this slide up and had a contractor that was very proud of himself that he's never had this much cracking in any one project. This happens to be a picture that shows all the types of cracking that you could get. So it was pretty impressive that he had that kind of pride. Let's talk about evaporation first. You know, the whole idea here is we know that we place our concrete initially, and then a lot of times people talk about the fact that you get bleed water, which is water rising up out of the concrete, and it sounds very space age and biblical or something. Things are rising and it's very exciting. The water isn't rising at all. Gravity is affecting everything in the system. It's just gravity brings everything else down a whole lot faster, right? So the aggregates sink faster, the cement sinks faster, and water kind of gets exuded and it stays up at the top of the system. This bleed water is actually protecting the system from undergoing a lot of shrinkage. As that starts to evaporate, now you start to see stresses building up in the system if the evaporation rate is too high. So if the bleed rate exceeds the evaporation rate, no cracking occurs. However, if you go the other direction and you don't get enough bleed but a lot more evaporation, now you start to get into the ability to build up stresses. So what you'll notice is if you have a plain system, and this is again very horrendous drawing of little tiny cement particles inside a fluid, they will actually settle right when your concrete shows up. So you don't know this, but as soon as the truck leaves and you got your concrete there doing its thing, that concrete already starts sinking. Right? It already starts settling. And what it's doing is these particles are essentially just starting to consolidate. Right? Once that bleed water starts to recede from that top surface, these particles actually start getting pulled together really tightly because of that capillary stress. As soon as that waterfront can no longer penetrate, those stresses exceed that strength and you get cracking. Now with lightweight, you get a very different type of behavior. You've got these fluid-filled particles, right, inside with these cement particles here. So even when the water gets down to this layer, before the stresses start to penetrate into the system, water is going to migrate out of the lightweight aggregate and come up to the surface to provide that protective film. So that water is going to do something very different than everything else we've been talking about up to this point, but it's going to sacrificially come up and start protecting that concrete. So it's going to give you a much longer time before those cracks are going to occur in that overall system. So what does that mean? Well, that means you can have substantial improvements. So here you can see a conventional concrete. This is about 1/4 of the water you'd use for internal curing. This is about half of the water. This is about 3/4 and the full amount that you use for internal curing. And this is the size, the number of cracks, and the size of the cracks that develop following an ASTM standard test. So what you'll notice here is when you use internal crack curing, you can substantially reduce plastic shrinkage cracking because it's sacrificially providing that water. Now, the real key takeaway is if you use this water to help you with plastic shrinkage cracking, you're not going to get some of those other benefits that we talked about that water. You can only use the water once, right? Once it's gone, it's gone. But if it helps you get through this period without developing those plastic cracks, it can be a dramatic improvement in the overall system. So again, concrete can be susceptible to cracking when it's restrained, right? Chemical shrinkage occurs all the time and it results in autogenous shrinkage. We use the lightweight to reduce the self-desiccation to hide the water, all right? And it can reduce shrinkage and plastic cracking as we talked about.